Consider the initial value problem. Y prime is equals to f of ty subject to the initial condition y at t naught is equals to y naught. I'm going to derive the local truncation error for Euler's method and then go on and find the order of the local truncation error for Euler's method. So we are having that ODE there. So I'll start by looking at the first question here, deriving the local truncation error for Euler's method. For Euler's method, if you still recall, yn plus 1 is equals to yn plus h multiplied by f of tn yn. So what we'll be looking at, if I just can illustrate them, if I have a number line, if we are starting at a point tn, then move on to a point tn plus 1. What would have there? We would have a yn, then go on to have a yn plus 1. For us to derive the local truncation error, I'm going to use the Taylor series expansion of y. So for the Taylor series expansion, if you still recall, if we have a function f and we are looking at the Taylor series expansion about the point t naught, the expansion is this one which is appearing on the screen there. But we want to suit this one to have the Taylor series expansion for the y that we are having. So wherever we are having f, we put y. So that would have y at tn plus 1 is equals to y at tn plus y prime at tn multiplied by tn plus 1 minus tn plus a half multiplied by y prime prime at tn plus multiplied by tn plus 1 minus tn squared. And the other terms, I did not write them because their value will be so small. But for the value of y at tn, we are saying it's yn, and the value of y prime now. But for the value of y prime, we have it here, y prime is f of ty. And the difference between tn plus 1 and tn, this difference here gives us the step size. So I can rewrite this equation to y at n plus 1 is equals to yn plus h multiplied by f of tn yn plus half multiplied by h squared multiplied by y prime prime at tn. And the other terms there, I did not include them because if our h is small, on the Taylor series expansion, if you can see, we'll be having up to the next one should have been h cubed, then the next one h to the power 4, then and so on. So if h is small, those values will be getting smaller and smaller. That's why we did not write them here. So that's the yn plus 1 there. Now for us to get the error, if you still recall, the error is the difference between the true value and the approximate value. So the approximate value is the one obtained by Euler's method, this one, and the true value from the Taylor's expansion is this one here. So for the truncation error there, it will be the difference of those two. And this pass will cancel out so that we remain with the absolute value of half multiplied by h squared multiplied by y prime prime evaluated at tn. So what you are seeing there is the error in a single step is proportional to the square of the step size of the h. If h is halved, then the local truncation error is roughly reduced by a factor of 4. So that's why I have in there, our truncation error is proportional to the step size h. I now move on to the next question there, finding the order of the truncation error. And the order or accuracy of a numerical method quantifies how quickly the error in the approximation decreases as the step size is reduced. So in this case, the error will be decreasing by an order of 2 because we're having a square there. So our order there will be 2. And we write it using this notation, order, then we have h squared. So that's the order there of the local truncation error. It's of order 2.